K is equal to 1. We're going to loop. I is equal to K. What's that value? K is equal to 1. I is equal to 1. How many iterations? 1 and 2. So 2 iterations. We'll exchange. We'll exchange what with what? 1 with 1. 1 with 1. Permute. K equals to 2. Exchange. 1 with 1. That means A with A. And call the string with 2. K is equal to 2. I is equal to 2. K is equal to 2. Exchange 2 and 2. Permute the string with 3. What's the value of the string? Cat. Goes with 3. Okay. Laser's getting very dull. That's the 3. And so K equals blunt. Ding, ding, ding. True. So therefore we print cat. We count 1. We don't recurse. We go back to after this call. Remember, we sent in what value again? That was 3. So now what's the value of K? When we come back. 2. So exchange 2 with 2. Now what do we do? We finished our recursion, so we're going to go back to. We're going to go to the previous version. K is equal to? So K is equal to 1. 1 is going to be exchanged with 2. Then we're going to push the value of K to 3, and then we're going to output CTA. So we're going to get all of the permutations out. You can run this code. You'll enjoy it. So what I did was, I took this code. Oh, did I do that? Okay. What I did was, I basically want to say, well, I'm kind of interested in how would you compute, for example, the unique permutations. Because I want to write the code, and the code is going to be right here. So this is the code for unique permutations. This is the modified code. It's basically the same code. Basically the same code. Right? So I have a unique start. Oh, this laser is done. All right, so I have a unique start and permute unique. Very, very similar. Notice that the first part here is the same. But then what I do is I basically have to store some information because I recognize the fact that if I have a letter and I exchange it with the same letter and I permute everything past the first letter, then it will not be anything different than I had if I didn't exchange it and I just permuted everything here. Tcat. If I say T and I permute all the CATs, I have 6 permutations starting with T. If I exchange T with CAT, I'm going to get the same thing out. So I want to make sure that I remember in my set, so I keep a set of characters of all the values that I'm putting in there that have been already exchanged. So in this case, what I have is else. I create a set of characters called LET for letters. And I create that, and they basically say if K is equal to I. So in this case, basically, what is K equal to I? That means that the characters I'm about to exchange are the same. If K is equal to I, or the character at I is not equal to the character at K, and the letter contains the character at I, what am I going to do in that case? So if K is equal to I, yes, then I'm going to go in, because I want to get all the permutations for a particular character. So for example, K is equal to I, Tcat. I want to exchange T with T, so I can get all those permutations. Okay? So if K and I are addressing the same letter, I need those permutations once. Because exchanging with myself is not exchanging with somebody else. I need those permutations once. So if K is equal to I, go ahead. If the character at I is not equal to the character at K, so that means that the ith character that I'm looking to exchange, K and I, if these characters are not equal to each other, and the letter contains the character at I. What does that mean? What does this exclamation mean here? I didn't read that correctly, so.
No.
So if the characters are different and I haven't added that into an exchange yet, then go ahead and add that letter to the exchange, exchange it, permute the unique, and exchange back. So I keep track of the characters. So for example, if I have a C, I'll exchange it with C. But if there's another C later, I'm not going to exchange it. If there's a C and there's an R, I'll exchange it with R, but I'll put it into the set. So if there's an R here, I'm not going to exchange it. So I'll only exchange this C with one letter exactly once. Because if I exchange it with one R, I'll get the same behavior as if I exchange it with an R. Okay, so the calculation looks a little bit weird. So basically what I did was, this is what we have here. What is this pi mean? That is the product, so it's going to be times. So I'm going to be multiplying a bunch of these things in here. I know you can't see my pointer. So I'm going to multiply here. So it's a very, very simple idea. S is a string. US is the number of unique characters in a string. Unique characters in a string, US. The bars is the length of the string. And L1, L2 are the first and second unique letters. LUS is the last unique letter. So TCAT, what's string? TCAT. What's US?
4. Awesome.
3, yep. And what's S bar? 4. What's first unique letter? T. And then C. And then A. And then the next one's a repeat. So what we're going to have is we're going to have a product of the number of characters in the string minus the sum of the unique letters in all the characters that came before this one. You're going to see this in a second. And this is a binomial coefficient over the number of letters. And I'll just show you what it's going to look like. So let's say we have a string S. And S is a string on top. So A, B, C, blah, blah, blah. Now, I make one observation. The number of permutations, number of unique permutations of that string is equivalent to the number of permutations of that string's permutation. So I choose a permutation that's especially useful for me, and I call S prime. I put all the A's, all the B's, all the C's, so I can kind of count them out. So what I'm going to have is, so this is going to be like, so what's the length of the string? 11. So notice that there are 3 A's, 2 B's, 4 C's, 2 D's. So it's going to be a product of binomials. So the binomials are 1, 2, 3, 4. You see them? So let's look at the first binomial. 11 minus, that's the length of the string, minus all the letters before this current letter. Since the first current letter is A, there are no letters, unique letters before that, therefore 11 minus 0. Binomial coefficient over 3. What is 3? 3 is the number of unique letters. Okay, so I take that, so that's going to be 11, choose 3, which is going to be 11 factorial over 3 factorial times 8 factorial. You know that deal. Now, the next thing I'm going to do, I'm going to take the letters, I'm going to consider the B's, but I take 11 and I subtract all the A's because they've already been accounted for. So it's going to be 11 minus 3, and then how many unique B's are there? 2. Now, the next one is 11 minus 5, because it's going to be 11 minus 3 A's and 2 B's. That leaves 11 minus 5, that leaves 6 over 4 unique C's. Finally, times 11 minus 9, because there are only 2 letters left, so all the other ones are 9. So 2 choose 2, and that will always be 1, by the way. So what we have is, when we do that, we get this multiplication of the binomials, 11, 3, 8, 2, etc. That gives me 63,300 for these values. Now, what was the length of the string again? The length of the string was 11. So how many actual permutations were there? If you take permutations, not unique permutations, but permutations, that would be 11 factorial. And we know that 10 factorial is about 3.6 million, so it's about 40 million. So with this string, from 40 million total permutations to 69,300 unique permutations. That's the formula, okay? And this is the code that you saw already. So the code is just a very small modification. Okay? And then what I do, then I did some crazy analysis that I'll show you a little bit. I'm not going to get into it now, but I'll just show you a little bit. So what I wanted to do is I wanted to look at the unique permutation analysis worst case. What's the worst case? What's the best case? Okay, is that the best or the worst? That's the best case, because we only have one permutation. If all letters are different, it's the worst. What's the average? Okay, so basically, so I do this, and I get into some fancy stuff here. Basically, we end up getting a very interesting result. Which is basically e plus 1 times n factorial. So that's the result, but then I did another analysis where I put some probability into it. And what I have here, we'll talk about it a little bit, but basically we end up looking at the probability of characters reoccurring. So for example, in the best case, the probability is 100%. In the worst case, it's 0%, that means they're all unique. So in general, we're going to say the probability is p. And it gives us a very interesting result. I'll show you a little bit of that. We end up getting this cool result, which is basically p to the n plus c times n factorial. And the reason that's interesting, because p is a probability. So if we're looking at an average case, the value of p must be what? Less than 1, which means that if we take a probability like 1/2, 1/4, 1/3, and we raise it to a long number like n, that p to the n is going to go to 0. But n factorial is going to go very quickly up. So actually we know that n factorial is growing towards infinity more quickly than p to the n is going towards 0. Which means that if we just were analyzing from a calculus standpoint, if we took the limit of this function, we would find out that t of n is really approaching what as n goes to infinity? It goes to infinity. But for realistic, interesting problems, we have interesting, realistic results. Notice that if probability is 0, we have Cn. It's probability of recurrence. So therefore, we're going to have C times n factorial. The worst case occurred when p is equal to 1.0, and p to the n is equal to 1, and therefore C is going to equal to E. And so this is a chart, and I'm going to show you this real quick. What I have here, and it's kind of hard to see, is that formula. You can see the string. These are for values of p, 10% to 100%. You can see that as we go to 100%, the number of permutations just go up very, very quickly. So these are the numbers. Yes, this is 13 million. Okay. And if p is restrained into values like 0.1, notice that 0.1 to the power of 10 is going to be a very small number. Going to be 1/10 billionth is what it's going to be. And the number of unique permutations probabilistically looks along that axis there. So anyway, I'm going to stop here. Look.